Hello students, I am Snehal Mule. Welcome back. This is our fourth virtual e-learning session on wave optics. Before we start today's session, let's have a quick recap of previous session. We discussed progress of a spherical wavefront and reflection of light at a plane surface. In this session, we will cover refraction of light at a plane boundary between two media and dependence of wavelength on the refractive index of the medium. Let us discuss refraction of light at a plane boundary between two media. Look at the figure. Mn is plane refracting surface separating two media, medium 1 and medium 2. AB is incident wavefront. PP' is normal to Mn at A. CE is refracted wavefront. Angle A'-AP is equal to R, angle of incidence. Angle P'-AE is equal to R, angle of refraction. Consider a plane wavefront AB incident on a plane boundary Mn, separating two uniform and optically transparent media. When A reaches at boundary surface, B still has to cover a distance BC to reach the boundary surface at C, as the wavefront is obliquely incident. Let at time t equal to 0, A just reaches the boundary surface, while B reaches the surface at C at a later time t equal to t. Let the wavefront at B require time t equal to t to reach the surface at C, then BC is equal to V1t, where V1 is speed of light in medium 1 and BC the distance covered by incident wavefront in time t, and it is equal to V1t. According to Huygens principle, when A reaches the boundary surface, it becomes a secondary source and starts emitting secondary wavelets in medium 2. During the same time t, the secondary wavelets originating from A travel in medium 2 and cover distance V2t, where V2 is speed of light in medium 2. Now we want to find the position of the secondary wavelets originating from A after time t. To find the position of the secondary wavelets originating from A after time t, draw an arc with radius V2t and center as A. We can draw arcs with each and every point on the surface AC. Different points along the incident wavefront reach the boundary surface successively between time t equal to 0 to t equal to t. If you observe the figure, you will notice that the radii of secondary wavelets gradually decrease from V2t to 0. The wavelet originating from A has radius V2t and the wavelet originating from C has 0 radius. The refracted wavefront will be the envelope of all wavelets emitted by all points between A and C during time t equal to 0 to t equal to t. CE is the tangent to the secondary wavelet emitted from A. The tangent touches the arc at E. AE is equal to V2t, where V2 is speed of light in medium 2 and AE is the distance covered by secondary wavelet from A in time t in medium 2. It is also a common tangent to all the secondary wavelets emitted by points between A and C. CE represents the refracted wavefront. See the figure. Angle A-AP equal to angle BAC equal to I. Angle P-AE equal to angle ACE equal to R. From triangle ABC, sin I equal to V1T upon AC. From triangle AEC, sin R equal to V2T upon AC. From equations 1 and 2, sin I upon sin R equal to V1 upon V2. Using n equal to C upon V, we can write V1 equal to C upon N1, V2 equal to C upon N2. Substituting the values of V1 and V2 in equation sin I upon sin R equal to V1 upon V2, we get sin I upon sin R equal to N2 upon N1. N1 sin I equal to N2 sin R. This is the law of refraction, where N1 and N2 are the absolute refractive indices of medium 1 and medium 2 respectively. N1 sin R equal to N2 sin R is Snell's law. From the figure, it is clear that incident ray, refracted ray and normal to the boundary surface all lie in the same plane. Incident ray and refracted ray lie on opposite sides of the normal. Laws of refraction are satisfactorily explained on the basis of Huygens wave theory of light. If V1 is greater than V2, N1 is less than N2, and I is greater than R, that is angle of incidence is greater than angle of refraction. For oblique incidence, the refracted ray bends towards the normal while going from optically rarer medium to optically denser medium. But if it travels from optically denser medium to optically rarer medium, it bends away from the normal. From the figure, it can be seen that the rays change their direction on crossing the boundary surface and image seems to be broken or bent. For normal incidence, the rays travel along the same direction and there is no breaking of image. The complete derivation is given here for your reference. Let us discuss dependence of wavelength on the refractive index of the medium. Let us consider a monochromatic light incident normally on a boundary between a rarer medium and a denser medium. The boundary is PQ. The three successive wavefronts AB, CD and EF, separated by distance λ1, are incident on PQ. λ1 is the wavelength of the wave in medium 1. As light is incident normally, it will not change its direction after refraction. A', B', C', D' and E', F' are the wavefronts after refraction. Consider that medium 2 is a denser medium. Hence, speed of the wave will be lesser in medium 2 than medium 1. So the wavefront will cover less distance in this medium than medium 1 in the same time. As a result of this, the wavefronts will be closely packed in medium 2. The distance between successive wavefronts is λ2 in second medium. λ2 is the wavelength of the wave in second medium. λ2 is less than λ1. So when the wave travels from rarer medium to denser medium, its wavelength decreases. The refractive index of the rarer medium is less than the refractive index of denser medium. From this, we can say that the wavelength of a wave is inversely proportional to the refractive index of the medium. The wavefront AB will reach boundary PQ at time t equal to 0. CD will reach PQ at time t equal to t. Let the speed of the wave in medium 1 be V1 and t is the time period in which distance λ1 is covered. Then we get t equal to λ1 upon V1. During the same time t, distance travelled by wavefront in medium 2 is λ2 and speed of the wave in this medium is V2. Then t is equal to λ2 upon V2. From equation 1 and 2, λ1 upon V1 equal to λ2 upon V2. Rearranging the terms in this equation, we get λ2 equal to λ1 V2 upon V1. As we know n equal to C upon V, we can write V1 equal to C upon N1, V2 equal to C upon N2. Substituting the values of V1 and V2 in this equation, we get λ2 equal to λ1 N1 upon N2, where N1 and N2 are refractive indices of medium 1 and 2 respectively. Now, if medium 1 is vacuum, where the wavelength of light is λ0 and the refractive index of medium 2 is n, then the wavelength of light in medium 2 is λ equal to λ0 V2 upon C, that is equal to λ0 upon n. we know V equal to nu lambda as ratio of the frequencies of the wave in two media can be written as nu1 upon nu2 equal to V1 upon lambda 1 divided by V2 upon lambda 2. As discussed earlier, V1 upon lambda 1 is equal to V2 upon lambda 2. We get nu1 upon nu2 equal to 1. This demonstrates that the frequency of a wave remains unchanged while going from one medium to another medium. Okay, now it's time that we test our understanding of what we have covered in this session and apply that to the next set of questions. So we have very easy questions for you. It is a MCQ. When a ray of light enters into water from air, you are given four options. You have to select the correct option. When a ray of light enters into water from air, its wavelength decreases. The next one. When light travels from one medium to another, its dash doesn't change. Again, you are given four options. You have to select the correct one. When light travels from one medium to another, its frequency doesn't change. Until next time, happy learning.